And this is going to be a foundation course for understanding a lot about links, and we're going to have a number of modules, but understanding PageRank is really the place to start. Because when I was on holiday this summer, a maths teacher approached me in a restaurant and asked me to explain the PageRank formula that was actually on my t-shirt at the time. And it's really the key to understanding Google's algorithms. And it made me think and try to create the best explanation of PageRank that I can find. And this is it. This is my presentation. And hopefully it's significantly stronger than others that you may have seen or may have heard. Of course, being a geek, I was wearing this matrix form of the PageRank algorithm, and it is the algorithm that made Larry Page and Sergey Brin two of the richest, most powerful people in the world. This is the maths that built Google. And reading it literally, it says, the PageRank of a page in this iteration equals 1 minus a dampening factor plus, for every link into the page, except for links to the page itself, add the PageRank of that page and divide that by the number of outbound links on the incoming page and reduce the overall amount by the dampening factor. Easy, right? Maybe for some of you, but this algorithm is fundamental in understanding links, and in particular understanding why most links actually don't count for very much, if anything, when it comes to internet marketing and search marketing and SEO in particular. And when you get to grips with the algorithm you see here, you're going to be light years ahead of most other SEOs. But I never really see it properly explained. And I guarantee that even if you know this algorithm inside out, you'll see some unexpected results from this maths by the end of this presentation. And you'll also, I hope, never use the phrase domain authority in front of a customer again, at least not in relation to links. What I would say is, in this presentation, in this module, I'm not asking anyone to understand much more than simple Excel. It looks complicated, but we'll get there, I promise you. So I'm going to start by showing you how that maths applies to this representation of a very small internet system with only 5 nodes. Then we're going to look at a slightly different map which has profound consequences for our results. So before we start, maybe have a look at this and guess which node has the highest PageRank. Okay? Have a guess A to E and see which one you think might have the highest PageRank. Okay, let's move on. The PageRank algorithm is called an iterative algorithm. So that means we start with some estimates and then we continually refine our understanding of the ecosystem that we're measuring. So how can we see how this formula applies to this ecosystem? Well, firstly, we need to create a matrix. So I've just put the little ecosystem, small internet, up in the top right hand corner so that we can concentrate on the maths. So firstly, we need to create a matrix. We have nodes, A to E. I'm going to call them, I guess we should call them pages for now because it's a terminology that we all understand. But the hardcore fans should know that I mean nodes, and this will be important later. So the first thing that we do is create an initial estimate for PageRank, and in my case, I'm going to put in the number of links the number of backlinks going into each page. Most people actually make an initial estimate for PageRank of 1 for every single page on the internet and then run through the maths. I've found that that's not as good. I think it's better to put in the number of links coming into a site or a page because it's a better estimate given no other information about the value of the pages, and it stabilizes the algorithm in less iterations, so you actually have to do less work. And it's also useful to check my spreadsheet, which we'll come to in a second. So node A has 1 link coming into it from page C, B has 2 links coming into it, C has 2 links coming into it, D also one link coming into it from page E, and then E has 2 coming in from it, one from page C, and actually it's got 3 coming in from D to E, but we record that as 1. And similarly, the outlinks, D looks like it goes out and links out 1, 2, 3, 4, 5 times, but in actual fact it links out to B and it links out to E. So I'm going to put in the outlinks under D a 2, not a 1, 2, 3, 4. Now we have to fill in our matrices and find all the spots where there's a link from one site to another. So we map out all the blanks in the matrix. Firstly, we can say that no page can link to itself. Well, of course it can link to itself, but within the Google's algorithm, within the PageRank algorithm, we don't count pages linking to themselves. So we put a red bar through all the pages linking to themselves. But then page A, as we go down to the next line, links out once. The number of outlinks to page A is 1, and it links out to just page C. So I'm going to put a green box on the A to C link. And then on the next line, B is linking out again just once, just to page C. Page C itself links out 3 times to pages A, B, and E. Page D links out to page B. So page D links out to page B. And it also links 3 times out to page E, but because we're working in a 1 or 0 system, it either does link or doesn't link. I'm going to call it 1 link. Okay. And then page E links out once to page D. So then we fill in our other boxes. There aren't any links on any of the other cells in our table, so we can make those red, and now we can use these green boxes because we've mapped our internet into a small matrix, and we can check a few things here. There's 8 green boxes, which is the total number of links in our algorithm, assuming that we're only counting the 3 links from D to E as 1. Also, note that the majority of the grid is red, because most of the pages on the internet just don't link to each other. So we now have our map and we can start to fill things in. Now, as we said, we're going to start by making the number of inbound links an estimate of PageRank. So I'm going to change the top line. Instead of calling it backlinks, I'm going to call it PageRank. So we've got an initial estimate for each page. So we think that maybe page A has a PageRank of 1, page B has a PageRank of 2, etc., etc. Okay. We also have a dampening factor, and most papers tend to talk, if they do talk about what the value of the dampening factor is, they talk about 0.15. So it's a number between 0 and 1, and this is the amount of dampening that comes into every page to stop the algorithm from going completely off into oblivion. So the multiplier is actually 1 minus that dampening factor, and I need to slip that into the sheet as well. So the multiplier is equal to the PageRank of the page times the dampening factor divided by the number of outlinks. So if I slip that in, we now have a multiplier here for each of our nodes. So 1, page A is 1 multiplied by 0.85 because the dampening factor is 1 minus, the multiplier is 0.85, which is 1 minus 0.15, the dampening factor. But on page B, we've got 1 outlink coming out, but 2 going. But we have a initial PageRank of 2, so it's 2 times 0.85, not 1.185. So the multiplier then turns out to be 1.7, and so we go along. So now we've simplified the formula. It's not so scary, is it? We can add the multiplier to each column as we go down. this is how much of its value is passed on to each of the pages that it links out to. So page A, when it links out, will pass on a value of 0.85 to wherever it links to. Whereas page C, even though it starts with a page rank twice as high, will only pass out 0.566666 recurring to any link, because it's got 3 links going out instead of 1. So on page C, the page rank equals 2. The multiplier is 2 times 0.85, all divided by the 3 outbound links. This means each one lends a score of 0.566666 recurring. Now this presentation isn't going to look at the case of when the outlinks is 0, because if you look at the formula on the right hand side, we have to divide our numbers by the number of outlinks. So if there weren't any outlinks, then that would theoretically mean that the calculation would become unstable. And we'll run a different module just to explain exactly what happens with 0 outlinks, or what some papers call dangling nodes, and some patents call there's a dangling node patent, which we'll touch on in another module. So now we can go along the green boxes, filling them in. So page A gives 1 link to C. Each link it gives has a value of 0.085, so we put 0.085 in the box along AC. Page C links to 3 pages, for example, giving 0.56 recurring to each one, and so on until all the green boxes are filled. Now if you remember, we took off the dampening factor before we started all this, so we need to add back the dampening factor to every page. So the 1 minus dampening factor of 0.15 we need to add back in, and we need to do this to make sure that the amount of page rank will stay stable. So the notion of page rank is a constant on the internet. So if you have a fixed internet and you assume that you don't create pages or take pages away, then every time you do the calculation, the overall amount of page rank that exists will be constant. This is interesting because the more spam you create, the more it pushes the important stuff up to the top, and also if you keep it all constant, then you know whether you've made an error at the end, because your page rank should be constant all the time. So now our final line on the iteration is really simply an addition of all these. So we can now work out what the new page rank is for each of our pages. So page A is 0.5 and all the 6's recurring plus 0.15 equals 0.716 recurring. Page B is 0.56 recurring plus 0.425 plus 0.15, making an overall page rank of 1.14. C ends up as 1.85, as does D, and then E ends up as 1.416 recurring. And that's actually all there is to the PageRank algorithm, except that I did say that it's iterative, so you need to do it again and again and again to get the real page rank for every page. So what I did then was I cut and paste the values that I've got into the bottom line of this matrix back into the top. And if you want to see the spreadsheet I was using, here it is. And so I cut and paste the line at the bottom, put it back into the top, it redoes the maths, and then I start to record line after line of iterations. And it's quite interesting to see what happens. Take the numbers at the bottom and put them in at the top, cut and paste, and after a number of iterations we get a second iteration, turns the numbers around again. So all of a sudden A goes down, B goes up. Third iteration, the page ranks change again in the bottom line, 0.74, 1.457, 2.6, 1.76. And then if I do that again and again and again, you can see that after the 15th iteration, in fact well before the 15th iteration, the page rank has stabilized and we've got set numbers for our page ranks. And now we've done our maths. and now we have a stable set of numbers, we can see which is the most important page on our internet. And in this case it's C. Was that the one you guessed? Well, whether you guessed yes or no, it's now time to reveal the wider story of how PageRank works. So you'll recall that I started by saying nodes instead of pages. And that's because this was doing the PageRank at the lowest common denominator that we had, which was at 5 nodes. But what if these were actually domains, web domains, not pages? And what if I now put in the pages for each domain, and then we start again? So now we have 10 nodes because we have 10 pages. We've only got 5 websites, but more importantly, we've also got some internal linking within the websites. And it's important to understand that PageRank uses internal links just in the same way that it uses external links. So you have to also be able to see the internal links to be able to understand PageRank. Where do you think the power will lie in this version of the internet? Am I mad enough to do the calculations all over again? Hell yeah. Of course I am. I won't go through all the pain for you, but this is how the numbers changed over time when we've got 10. And this is the updated numbers. And if you want the whole spreadsheet, that's fine. You can get the whole spreadsheet by emailing talk@dixonjones.com with PageRank in the title, and we'll be able to get the spreadsheet to you for both the 5-node model and for the 10-node model. And in this one, the winning one is site E, E1 I'm calling this, page 1 on site E, 5.71. So this produces some really interesting observations. The winning domain was site C in the 5-node model. So if you had used the domain level modeling, you would probably have hoped for links from site C, and you could potentially have got links from the weakest page on the internet. And this is why you should always look at the strength of a page on the internet rather than looking at the strength of the domain. So here we've got the two pictures side by side, one at the page level and one at the domain level. You'll see we had a score of 2.403 for the 5-node model in site C, but actually page E1 is the best one if you wanted to get a link. And it's very hard to see that. The internal links, it turns out, are something that you cannot control dramatically. The internal links on a site that you cannot control dramatically affect the PageRank of your own pages. This is very, very interesting. Also, you have to understand that PageRank was only ever done at the page level. Majestic does the calculations at the top level, subdomain level, and page level, as does as does Moz. Ahrefs do it in a different way. They don't use a PageRank concept in their algorithms. And in the quest to show our customers higher link counts, Majestic and I'm sure Moz have defaulted to putting the top level domain counts first. So we have a tendency to look at domain level statistics. But it's the page level that counts, not the domain level. So that's observation 1. Observation 2 is if you build a new site and you only had domain authority to understand where your links would come from, you could easily have got linked and linked your website from the worst possible page on the internet. So this happens because of internal links. So how on earth are you going to be able to see the strength of a link if that link strength depends on the internal links of an entirely different website? You really do need to have a machine that understands the whole of the internet to be able to do this. The next observation is the idea that the data doesn't have to be complete, but it works best with the universal data set. So back in 2014, one of the researchers at researcher in Toulouse, French researcher, did some work and did the maths, the PageRank maths, just on Wikipedia itself. So it wasn't understanding any of the internal links to Wikipedia, any of the links into Wikipedia, but it did look at all the links within Wikipedia itself to itself. And doing the maths there, the research carried out by Young Ho Om found that the Swedish botanist Carl Linnaeus was more influential than Jesus. And when you do an algorithm check on the whole of the internet or a wider internet, you find a different result. So the things that we can find out here is that every signal, a link signal, is very, very small, and individually a link is prone to error or opinion. The good news is that as you get a broader and broader understanding of the internet, that error at scale decreases, and your confidence in whether a page is strong or not increases in the algorithm. The next oddity is that the majority of pages have hardly any PageRank at all. The top 3 pages in our 10-node model account for something like 75 to 80% of the entire PageRank of the system. So E1, E2 and D3 account for 75% of the total PageRank. That's converting the numbers in the top right hand corner to areas on the chart. But if we'd used our original estimate of link counts for PageRank as a final analysis, then this would have been a terrible, terrible mistake. Using link counts turns out to be a terrible proxy for PageRank. So in our initial estimate, we said that C3 was our most important link. C3, E1 and E2 all started with PageRanks of 2 because they had 2 links going into them. But if you have a look at C3 in the final analysis in the bigger rectangular area, you'll see there's a tiny amount of PageRank. So it's gone from the most important to the least important. So when we started, page C3 was our best guess for highest PageRank. But look at how much PageRank or love it lost at the end of the PageRank modeling process. And our PageRank doesn't link. In both versions of my model, I used the total of my initial estimate to check my maths wasn't going south. After every iteration, the PageRank remains the same. This means that PageRank doesn't leak. This is interesting because 301s can't just bleed PageRank. Otherwise, the algorithm might not remain stable. On a similar note, of course, pages with a 0 outbound link can't be fixed by dividing something other than 0. Now, they do need to be fixed, but not by diluting the overall PageRank. And I will try and look at this and other cases in other modules in my training sessions. I would like to look at the reasonable behavior model, the reasonable surfer patent. I would like to look at dangling nodes. I then, once we've really understood how links count, I want to look at how search engines crawl and understand and interpret the data, and how they don't just hop from page A to page B to page C. Then we'll look at link building strategies, and then we can understand that in context, and perhaps we can avoid some of the big traps that a lot of people jump into. I hope that you'll try some of my course. I'll leave you with these thoughts. I did a 10-page calculation here. 10 times 10 calculations, and then 15 iterations was 1,500 bits of maths. Imagine if you're doing the same sort of calculation with trillions of pages, and then trillions and trillions and trillions of bits of maths. The point is that PageRank proxies, building a PageRank proxy machine, is hard, which is why so few companies have tried to do it. And it's also one of the reasons why Google can't let it go. This is a tweet from Gary in 2017 saying, "Do you know that after 18 years we're still using PageRank and hundreds of other signals in ranking. So this training course is going to be a bit different. It's going to take you through these processes. It's going to take you through the patents, through what we know and what we can deduce. I hope you'll join me, and I hope you had a good time listening to this presentation. Thank you very much for your time.